Hello dear students, welcome back to our YouTube channel. As you know that we are studying about inverse Laplace transform. In previous lecture we have seen the linearity property. In linearity property we have two functions f1 of s and f2 of s, which are Laplace transform of f1 of t and f2 of t respectively. And the theorem says we have to prove inverse Laplace transform of c1 f1 of s plus c2 f2 of s is equals to c1 f1 of t plus c2 f2 of t. We have just used the definition of Laplace transform of f1 of t and f2 of t, and applying inverse Laplace transform on both sides, we will get inverse Laplace transform of f1 of s is equals to f1 of t, and inverse Laplace transform of f2 of s is equals to f2 of t. By using linearity property for Laplace transform, we will get Laplace transform of c1 f1 of t plus c2 f2 of t is equals to c1 Laplace transform of f1 of t plus c2 f2 of t by using the property of linearity property. Correct? And to this equation we have applied inverse Laplace transform operator, by which we have cancelled inverse Laplace and Laplace transform. We have c1 f1 of t plus c2 f2 of t, and in next we will get c1 or inverse Laplace transform of all these. Correct? Since inverse Laplace transform operator is distribute over addition and subtraction, so we have inverse Laplace transform of c1 f1 of s plus c2 plus inverse Laplace transform of c2 f2 of s. Correct? And since c1 and c2 as given in theorem, c1 and c2 are constant, so taking constant outside, inverse Laplace transform of f1 of s plus c2 inverse Laplace transform of f2 of s, it is the required proof of our linearity property for inverse Laplace transform. Now we will see shifting theorem for inverse Laplace transform, and the shifting theorem is stated as let inverse Laplace transform of f of s is equal to f of t, shifting theorem. If inverse Laplace transform of f1 of or f of s is equals to f of t, then inverse Laplace transform of f of s minus a is equals to e raised to at f of. We have to prove inverse Laplace transform of f of s minus a is equals to e raised to f of t. Correct? Now we see how to prove this. Since we know Laplace transform of f of t is equals to integration from 0 to infinity e raised to minus st f of t dt, and it is equals to f of s. Correct? F of s, or we can say that f of s is equals to integration from 0 to infinity e raised to minus st f of t dt. Is it right? Yes. Now replace. Now Now replace s by s minus a. So we will get f of s minus a is equals to integration from 0 to infinity e raised to minus s is replaced by s minus a t f of t dt. Correct? Now we have f of s minus a is equals to integration from 0 to infinity e raised to minus s t minus a plus a. So it's minus and this minus become plus, and we have f of t. Now we have integration from 0 to infinity e raised to at e raised to minus st f of t dt. We have e raised to minus at f of t dt, or we can write it as 0 to infinity e raised to minus st e raised to minus at into f of t dt. Correct? We have the function e raised to at f of t, and integration from 0 to infinity e raised to minus st dt will come to inverse Laplace transform of e raised to at f of t. Correct? So we have f of s minus a is equals to Laplace transform of e raised to at f of t. Correct? Now, since by using the definition we have the Laplace transform operator, so we replace this sign by Laplace transform. Now applying inverse Laplace transform on both sides, we will get inverse Laplace transform of f of s minus a equals to e raised to at f of t dt. Hence the result, we have the result here. So whenever we have a function or a function having operator s minus a where a is any constant number, so we can directly write e raised to at f of t, and we will get the inverse Laplace transform of this f of s minus a is equals to e raised to at f of t. Now if we have here Laplace inverse Laplace transform of, if we have f of s plus a, if we have s plus a, then we will get inverse Laplace transform of f of s plus a is equals to e raised to minus at f of t. There is no big deal, just if we have s minus a, we will get e raised to at, and if we have f of s plus a, we will get e raised to minus at f of t. Correct? Now I think it is enough today. We have proved the shifting theorem, in which we have if inverse Laplace transform of f of s is equals to f of t, then we have to prove inverse Laplace transform of f of s minus a is equals to e raised to at f of t. It is generally called shifting theorem, first shifting theorem. Either they may ask to prove this by giving this statement, or they will ask you write a statement and prove first shifting theorem. We have to write the statement first, then prove of that theorem. And by using the simple definition of Laplace transform, we have studying I think from 10 to 12 days. the definition of Laplace transform, that is Laplace transform of t is equals to integration from 0 to infinity e raised to minus st f of t dt. By using this definition, basic definition of Laplace transform, we can convert this by applying inverse Laplace transform and replacing s by s minus a, and after replacing we can simplify that integration and taking e raised to at and f of t as a function, whole function, and the term integration from 0 to infinity e raised to minus st dt replaced by the symbol Laplace transform operator and the function as it is. Now shifting this Laplace transform to left hand side or applying inverse Laplace transform to both sides, we will get inverse Laplace transform of f of s minus a is equals to e raised to at f of t. It is the result for inverse Laplace transform of s minus f of s minus a. We will get e raised to plus at. Correct? Whenever we have f of s plus a, we will get with minus sign e raised to minus at f of t. And this is the required result for first shifting theorem. Here we can write it as first shifting theorem for inverse Laplace transform. For inverse Laplace transform. Correct? For inverse Laplace transform we have already studied. For Laplace transform also. Now we have seen about the first shifting theorem for inverse Laplace transform. In next lecture we will try to solve the second shifting theorem and other theorems. Till then, keep watching our videos and stay connected with us. Thank you. Bye.